In our last video, we left off with this example 3, and I did not do this bottom problem, so I want to make sure I go back and look at that. We had shown that the two triangles at the top were congruent based off the side angle side theorem, and we want to now show this at the bottom. These two triangles are congruent. Now this one is a little bit different because it's not just very plainly labeled, okay, this is the same as this or whatever. So we've got to again kind of think a little bit here. Now notice that it does tell us that these two triangles are these two side lengths AB and DC are parallel. Okay, so that's going to be important because if they're parallel, then that's going to give us some good information. Now, we can start very basic. We can show very easily that side length AB, or segment AB, is congruent to segment CD. Now, you may say, well, how do I know it's CD and not DC? Well, because if you think about from angle A, if you were to turn your screen where angle A is at the bottom, well, that angle A has that side length of 6 to the left. Okay, so think about that. Twist your screen. You can look at that if you're doing this on a phone or tablet. With angle C, if you look at it the way it is on the screen, you see that length of 6 is to the left. And so that means that angle A and angle C need to correspond, and then angle D and angle B also need to correspond. Now, we want to show they're congruent, not equal. So there's a side length. We also know that this segment, this diagonal from B to D, this dotted line that you see on the screen, we also know that that is congruent in both triangles. And so we could say that segment BD is congruent to segment DB. Now, why did I switch the letters up? Well, again, if we're talking about this triangle at the top, ABD, so this one here, talking about that triangle, well, from angle A to angle B, you have that length of 6, right? And so from angle C to angle D, you have the length of 6. This angle and this angle would be the ones that correspond. So we don't want to say BD is congruent to BD because we're talking about two different triangles here. And so, again, the order has to matter. And you can really say that with our previous statement because we said that angle B and angle D would have to correspond based on that statement. So again, just want to make sure we have those in the right order. Now, we've shown that two sides are congruent. We've shown this side and this side with the 6. We've also shown that this side is congruent. Now we need to show that their included angle, the one that I've marked here, is congruent. And so if these two segments, AB and DC, are parallel, and that means that this dotted line is a transversal. And if you remember, we talked about transversals back in chapter 11, and we said that if two parallel lines are cut by a transversal, their alternate interior angles have to be congruent. Well, that's exactly what we have here. This angle D, or let me name it CDB, this angle, that angle is an alternate interior angle to angle ABD, this one. And so since they're alternate interior, then they have to be congruent. Again, that's based off of our knowledge of parallel lines cut by transversal. And so we're going to then say that angle ABD is congruent to angle CDB. Again, make sure we have all of our letters in the right order. And so, again, based on the fact that it's side angle side, because that angle is included, it's the one between our two sides. Because of that, these two triangles must be congruent by side angle side. Okay, again, when you do this problem solving, you do these proofs, you've got to pull in, what do I know? What are things we've learned before that I can pull in to use in helping me prove that this is true? We don't make assumptions. We only use definitions and only use things that we can prove. Okay, so that's really key when we get into, especially in 12.2, where we really get into the proofs in some detail. And so you can see that there. We've got that statement about the alternate interior angles, and we've shown the two sets of segments are congruent, and so the triangles must be congruent. Now, let's add another theorem to our list that allows us to know that triangles are congruent. So the theorem is called the hypotenuse leg theorem. Now, if you're not familiar, in a right triangle, where this is the right angle, this side is the hypotenuse. The other two sides are what we know as the legs. That's those two sides. And so what this theorem says is that if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and the corresponding leg of another right triangle, then the two triangles have to be congruent. Again, this is something we could prove. We're not going to. That's a little higher level than what we're getting into in this class. So we're just going to take that as a fact that this theorem is true, and may use that if we need to. So again, as we're getting into proofs, again, that's what's coming up here in the next section. As we get into that, we want to make sure that we are kind of keeping a log of all these things to show triangles are congruent, because that's what a lot of what we're going to be talking about here over the next section is going to be. And so hypotenuse leg is a theorem that we may use. We could use the side-side-side theorem. We could use the side angle side theorem. And there are some others that we'll add to the list as we go, but those are the ones we've seen so far. And by the way, before I move off of this one, I will tell you that this one is can be proven based off the Pythagorean theorem that says that a squared plus b squared equals c squared. And so if this is a in each triangle, and this is b, and this is c, well, if we know that a is the same, and we know that c is the same, well, then we could solve that equation and find out that this b can only be one thing, right? And so that's how you would go about proving this. You would use that Pythagorean theorem. Again, we're not going to worry about the proof. I just wanted to kind of mention that to kind of help you maybe understand, well, that makes some sense, where if this is a right triangle based off that theorem, this is something that's true. Okay? Again, the Pythagorean theorem is something that we could even prove, and any theorem that we talk about can be proven. And so we could do that. But what we're going to do for a lot of this is just kind of think about it from an intuition standpoint, and hopefully intuitively a lot of this stuff kind of makes some sense for you. All right, so we got a few properties here for isosceles triangles that we're going to talk about. And again, specifically isosceles triangles. But before we get into that, I need to define for you an angle bisector. So an angle bisector is a ray from a vertex that divides the angle into two congruent angles. For example, if you were just to draw an angle, any angle, doesn't matter, the angle bisector is the ray that comes out of that divides this into two congruent angles. So if you were to think about it in a triangle, for example, you have three angle bisectors. You've got that one, you've got this one, and then that one. And so there's some different properties that we can talk about with angle bisectors, and I'm not sure that we're going to get into all of that. As a geometry teacher in high school, this was always really fun because you could do different activities with this. In this case, just to throw this out, this point where those all intersect would be the point that you could balance this triangle on. And so that's kind of a cool thing to be able to draw one, maybe cut it out and be able to show that, at that one point, this this triangle would be balanced. And so just some really neat things that can be done as if you were to end up teaching a geometry class or a unit on geometry. I would encourage you to look for activities that make this stuff make sense. Again, if we were in class together, in our current format being online, it's hard to show you a lot of this stuff, where if we were in class together, we could look at a lot of hands-on things. We could do some activities that I think would be really cool that would help make some of this make sense for you. So just be aware of that as you are going to be a teacher. You may teach a unit on geometry. Try to tie in a lot of those different things. I think that'd be a really neat way to teach this geometry. So if you understand that, then this next theorem is gonna make some sense for you, I hope. It says that any point equidistant from the endpoints of a segment on a perpendicular bisector of the segment. So any point equidistant from the endpoints of a segment is on the perpendicular bisector of the segment. Now, again, this theorem applies to isosceles triangles. So remember, in an isosceles triangle, you have two side lengths that are the same. So this side and this side would be side lengths that are the same. The angle bisector here in an isosceles triangle is going to be perpendicular. If it's perpendicular to the opposite side, this is what we call a perpendicular bisector. Okay? And so what it says is that any point that is equidistant from the endpoints of that segment, this segment, okay, any point that is equidistant from that is on that perpendicular bisector. For example, if you were to say, well, what about this point? Yep, that point is equidistant, same distance, to that point. What about here? Yep, that segment and that segment are the same distance. You can do that with the vertex, this point, and you can see that, again, it's isosceles, so we already know those two side lengths are the same. And so what this theorem tells us is that if there's a point that is on a perpendicular bisector, that's the key word here, then those points are all equidistant from this segment. We'll call it segment AB, just have a reference. So every point along this perpendicular bisector has to be equidistant to point A and point B, the end points of that segment. Okay, again, that's another theorem that could be useful to us as we move forward. Now, I'm going to erase that because there's another theorem that's going to come across the screen here. So let me erase that triangle so you can see the next theorem. So the next one says that any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Really very, very similar to what we just said. Okay, so the one above it says any point equidistant from the endpoint is on the perpendicular bisector. Well, this says the opposite of that. It says, or the converse of that, it says that any point on the perpendicular bisector is equidistant. Okay, so again, let me make sure you're clear on this. So we've got this triangle. We've got a perpendicular bisector. The first theorem, that one, says any point equidistant from those endpoints is on that perpendicular bisector. The second one says that any point on that perpendicular bisector is equidistant from the endpoints of that segment. Okay, so they're very, very similar. One just says that all the points on that perpendicular bisector are equidistant. The other one says that if there's a point that's equidistant, it is on the perpendicular bisector. Okay. If you have questions with that, I can always answer emails or do a Zoom session with you to make that make more sense. All right, so let's look at two more theorems that deal with isosceles triangles. So the first one says the angles opposite of congruent sides are congruent. Okay, again, in a base and in a isosceles triangle. Okay, if this is isosceles, it says the angles opposite the congruent sides. So opposite of this side would be that one, and then opposite of this side would be that one. And so it says the angles opposite the congruent sides are congruent. That means that this angle and this angle have to be congruent. That's what we know as the base angles. In fact, when we talked about isosceles triangles in chapter 11, one of the things that I told you is that the base angles were congruent. Okay, so if you understand that isosceles triangles have two sides that are the same length, then their opposite angles are also going to be congruent every single time. And then our next theorem says that the angle bisector of an angle is formed by two congruent sides. The angle bisector of an angle formed by two congruent sides contains an altitude of the triangle and is the perpendicular bisector of the third side of the triangle. Now, that probably doesn't mean a whole lot to you, so let's kind of take that apart. Again, talking about an isosceles triangle here. And I'm going to show you a diagram of this in a second. So we've got an isosceles triangle, and it says the angle bisector of an angle formed by the two congruent sides. So that means this angle bisector contains an altitude. So we haven't defined altitude. We'll do that in a second. Essentially, that's the height of that triangle. So if you were to take, let's just say, this triangle, for example, it has three different altitudes. The altitude is the overall height, where if you were to draw a line from each vertex straight down to the opposite side where it's perpendicular, you would have your altitude. So there would be one that would go here, and then from this side it would go out this way to this point, or this segment. No, I'm sorry, went the wrong direction. So if you were to extend this out, it actually would go out here, where that's a right angle. And so you could extend each of these altitudes, and they all intersect at the same point. And so what this says is that the angle bisector formed by the two congruent sides contains an altitude of the triangle, and it is a perpendicular bisector of that third side. So the altitude and the perpendicular bisector end up being the same in an isosceles triangle. So let me show you this. There's our definition of altitude. So an altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side of the triangle. And so you can see in this first example, all the altitudes are inside the triangle. Okay, so you can see that where this altitude, and this altitude all come together at one point. In an acute triangle, that's going to happen. In an obtuse triangle, that point is where they all meet is going to be outside the triangle. And so again, is the an altitude of a triangle is the perpendicular segment from the vertex of the triangle to the line containing the opposite side of the triangle. And again, they all intersect at one point. So that too may be something that helps us when we get into these proofs in section 12.2. Again,